Hello, my name is Jordan Pries. This is my lab report 3. My student ID is 7857106. And here is my student ID just to verify. And next slide, I have a picture of it. Alright, so question 1 is about liquid-liquid separation. So question 1 is asking the difference between washing and extracting in a liquid-liquid separation context. It's first necessary to understand what a liquid-liquid separation is. So you use liquid-liquid separation to purify or separate mixtures of different components. So you have a mixture of different components and you separate them. You start off by taking two solutions that have limited solubility in each other but can each dissolve a different component of the unknown mixture. So a common example is when you'd have like an organic layer and an aqueous layer. So washing and extracting have the same general procedure. The only difference is what you're removing from the mixture of solutes. So in a washing, what you would do is you would dissolve the mixture and put it in a separatory funnel, and then you would add the washing solvent to the separatory funnel, and then you would mix them together in the separatory funnel and remove the washing solvent alongside the unwanted solutes, and you would leave the desired solute behind. So a common example of this is washing dishes, in which case you use soap, the solvent in this example, to remove dirt, which would be the solutes in this example, the unwanted solutes, and you leave the dishes behind, which is the desired solute. So in an extraction, it's the same procedure of adding a solvent and mixing in the separatory funnel and then removing the solvent, but in this case, you're using the extraction solvent to remove a desired solute from the dissolved mixture, and you're leaving the unwanted solutes behind. So it's the opposite of washing in a sense. So it's most commonly used to separate an organic base or an organic acid from an organic neutral by dissolving the base or the acid in an aqueous layer and leaving the neutral in an organic solvent. And this way you could isolate each solute. So an example in everyday life is making tea or coffee. The flavor compounds are extracted from the leaves or the plants or the beans, depending on tea or coffee, but the unwanted solutes, the beans, the leaves, the plants, whatever it is, they're left behind in the filter or whatever. So you're just left with the flavor compounds. For question 2, my last name is Pries, so I had unknown mixture 3, which contains caprolactone, acetic acid, and benzoic acid. I've obtained relevant data and figures from PubChem, including their solubilities in different solvents. It should be noted that I was unable to find much information on caprolactone after hours of searching, so this analysis might not be fully accurate. The main thing observed in this comparison on this slide of solubilities is that caprolactone and acetic acid are soluble in water, and benzoic acid is only soluble in hot water. It's insoluble in cold water. And we also note that acetic acid and benzoic acid can both be deprotonated, and as you'll see later, it is relevant for acetic acid. So the relevant properties from the previous slide can give us an idea of how to separate the components. For benzoic acid, we base it around the fact that it is the only compound not soluble in cold water. So the first thing we should do is to dissolve the mixture in water around less than 10 degrees Celsius to isolate only benzoic acid, which could then be filtered. After that, we'll most likely perform a liquid-liquid separation involving the deprotonation of acetic acid and the separation of an organic and aqueous layer to isolate acetic acid and caprolactone. Each compound could be further purified from there. We will now analyze a more thorough procedure for the separation of these three compounds. So, to start the procedure, the first step is to isolate benzoic acid. This is done by dissolving the mixture of solids in a beaker with ice water, so that the water would be around less than 10 degrees Celsius. This beaker could then be allowed to sit in an ice bath to ensure all the benzoic acid remains precipitated out of the solution, and then this solution could then be poured into a suction filtration, and the caprolactone and acetic acid would be pulled through the suction filtration, while the benzoic acid would remain on the filter paper. The benzoic acid could then be washed with ice-cold water to ensure that all the caprolactone and acetic acid are removed and pulled through into the filtrate. And I've created a diagram on the slide there which illustrates the steps that could be followed for the procedure of isolating benzoic acid. So then in step 2, we need to separate the caprolactone from the acetic acid, and to do this we'll use a liquid-liquid separation. So to start for this liquid-liquid separation, We'll start by adding the filtrate from the suction filtration in the previous step to a separatory funnel. This filtrate contains the compounds caprolactone and acetic acid, and they're dissolved in water. Then we will add an equal amount of hexane to the amount of water in the separatory funnel. This will dissolve the caprolactone and the acetic acid, meaning they will currently be in both layers. Next, we'll add concentrated sodium hydroxide to the funnel. We use concentrated sodium hydroxide because there's already water in the funnel, so if we were to dilute the sodium hydroxide, it wouldn't have as much an effect on deprotonating the acetic acid. Then once this has been added, we mix the funnel. This will deprotonate the acetic acid into acetate ions. These ions will be forced into the aqueous layer of water and sodium hydroxide as they are insoluble in hexane. Forcing all of the acetate ions into the aqueous layer will saturate the aqueous layer and will cause the caprolactone to prefer the organic layer of hexane. The separatory funnel will now contain a top organic layer with hexane and caprolactone and a bottom aqueous layer containing water, sodium hydroxide, and acetate ions. After mixing, we remove the aqueous bottom layer into a beaker and repeat with dilute sodium hydroxide multiple times, adding the sodium hydroxide and mixing and removing the aqueous layer to ensure that we remove all the acetate ions out of the separatory funnel. Then we'll combine all the aqueous layer collections into one beaker and empty the organic layer into a separate beaker. Which brings us to the next step, where we isolate both compounds from their solutions. So we need to isolate caprolactone and acetic acid from their separate layers. So to isolate the caprolactone, we start by adding the drying agent calcium chloride to remove any water remaining in the organic layer. Then you decant the organic layer, leaving the drying agent behind, and you pour the organic layer into a round bottom flask. Then you can use this round bottom flask and put it in the rotary evaporator to distill off hexane, which has a boiling point of 69 degrees Celsius, leaving the caprolactone behind. Next, to isolate the acetic acid requires a little more work, as acetic acid and water are very miscible and difficult to separate. The best way to separate acetic acid and water would be through an azeotropic distillation. Unfortunately, this equipment is unavailable in the organic laboratory. So we'll start by adding hydrochloric acid to the collected aqueous layer. This will cause the acetate ion to protonate or regain its hydrogen and turn back into acetic acid, using an equal amount of hydrochloric acid as NaOH used earlier in the liquid-liquid separation. Next, we use a simple distillation to boil off the water, leaving the acetic acid behind. Water boils at 100 degrees Celsius and acetic acid boils at 118 degrees Celsius. So the water will boil off first, leaving the acetic acid behind. This won't necessarily be pure, but a purification step is not necessary for this question, so this will be the end of the isolation of our compounds. So for question 3, I'm going to start by briefly discussing the reaction involved in the synthesis of 2-butoxynephthalene. Later I'll more thoroughly analyze the reaction mechanism. This is just to help understand the procedure. So this is a SN2 reaction. I will explain why later, but what this means is that the nucleophile is attacking the substrate as the leaving group leaves. So a nucleophile is a chemical species that donates an electron pair to form a chemical bond. So I've put in the slides the 2 intermediate steps involved in this reaction. So the first step is the conversion of 2-naphthol into a nucleophile. So you deprotonate 2-naphthol using a strong base, in this case NaOH, which converts it into 2-naphthoxide ion, which this is the nucleophile. And then in the second step, I've shown there the 2-naphthoxide ion attacks the 1-iodobutane, specifically at the carbon right next to the iodide. And so in this reaction, the nucleophile is the 2-naphthoxide ion, and the leaving group is the iodide. The nucleophilic attack in this reaction is step 2, where the 2-naphthoxide ion attacks the 1-iodobutane molecule. So then on to the procedure. So you start by adding 0.5 grams of 2-naphthol, 3 pellets of sodium hydroxide, and 5 milliliters of 95% ethanol, and a stir bead to a distillation flask, which I've illustrated there in the diagram. And then next you attach a condenser onto the distillation flask, and then you reflux, otherwise known as boiling, the solution till the solids dissolve. And this should be around 15 minutes, but you just boil it till the solids dissolve. And yeah, I've shown that in the diagram there. So the next step after that, you disconnect the condenser temporarily, and using a digital pipette, you measure exactly 0.50 milliliters or 500 microliters of 1-iodobutane, and you add it to the flask. Then you reattach the condenser and allow the reaction to reflux for about an hour to an hour and a half. And I've included a diagram there showing the process of the addition of the 1-iodobutane. And then after refluxing it for about an hour and a half, you'll use a TLC plate or thin layer chromatography to track the reaction progress in the products. So in this step, what you'll do is you'll take a small amount of the product mixture and you'll spot it on the TLC plate, and you'll also spot the reactant to naphthol, and as well as a co-spot to compare the two. And then you can use this plate to determine if there's any 2-naphthol left over in the products. And then the next step after this is the workup, which this is the step used to isolate and purify the product. So the workup for this reaction begins by quenching the reaction. So what you do is you're pouring the hot products that you've just finished refluxing, and you're pouring them over ice water in a beaker. So it should be noted here that 2-butoxynaphthalene has a melting point around room temperature, and it is also insoluble in water. So when you pour the 2-butoxynaphthalene in the ice water in the beaker, and you place this beaker in an ice bath, this cools it to close to 0 degrees Celsius. So this causes the 2-butoxynaphthalene to convert into a solid, and it's insoluble in water, so it precipitates out. So you do this just to isolate the 2-butoxynaphthalene from any impurities that may be in the mixture of products. So once it precipitates out, you use a suction filtration to separate the product from the rest of the solution. So the diagram shows there that you pour the mixture into the suction filtration, and the impurities and everything else is carried through with the water, while the 2-butoxynaphthalene remains on the filter paper in the suction filtration. So yeah, there's a diagram here displaying the whole process of the workup. And after the product is isolated using a suction filtration, the next step is to measure the amount collected and also record an IR spectrum for the collected 2-butoxynaphthalene. So next, we're going to look at a product analysis of all the data collected from the organic synthesis experiment. So first, we'll look at the TLC plate obtained from the experiment. So the plate was spotted using the product mixture on the R spot and the reactant 2-naphthol on the S spot, and then a co-spot containing both. And I've marked the spots in the picture of the TLC plate, and you can see that the R spot and the co-spot look identical. So this is indicating that the product mixture contained leftover reactant 2-naphthol. So what this indicates is that the reaction did not carry out to completion, as there was still reactant left over. And this is also a good indicator of why we do the workup, because there was leftover 2-naphthol with mixing with the products. So the workup is to isolate the product from that leftover reactant. So next we look at the IR spectrum obtained of the isolated product. So I've marked relevant signals on the spectrum and obtained reference values from the lab manual for each relevant signal, and we'll analyze each group now. So on the far left, we see a small signal between 3000 to 3100 wave numbers. So this signal is characteristic of sp2 carbon-hydrogen bonds, and in the case of 2-butoxynaphthalene, this would be the carbons in the aromatic rings. There's also a group of signals between 2850 and 3000 wave numbers. So this is characteristic of sp3 carbon-hydrogen bonds. So this is important that the signal is present in this IR spectrum, because it's indicating the presence of the hydrocarbon chain attached to the ester oxygen. So next we see 4 important signals that indicate that there's 2 aromatic rings. So aromatic rings show up as 2 signals, one around 1600 and one around 1450, and we see 2 sets there around those numbers, which indicates that there's 2 aromatic rings, which in this case, this would be the naphthalene component with those 2 aromatic rings. We also see 2 signals between the 1000 to 1100 range, which is characteristic of carbon oxygen bonds, and in this case, this would be the ester oxygen and both the carbons attached to it. So this is not a diagnostic signal as it's in the fingerprint region, but the presence helps to confirm that there is an ester oxygen, which helps to indicate that this is 2-butoxynaphthalene. So It can be concluded that it is 2-butoxynaphthalene in this IR spectrum due to the fact that we have sp3 carbon-hydrogen bonds as well as carbon-carbon double bonds, more specifically the aromatic ring carbon-carbon double bonds, because in the reactants you would have had the aromatic ring showing up for the 2-naphthol and the hydrocarbon bonds showing up for the iodobutane, but you wouldn't have had both showing up in either of those. So the fact that there's both in this IR spectrum indicates that this is 2-butoxynaphthalene. So moving on to the final part of the product analysis, we're going to look at the product obtained, specifically the yield of 2-butoxynaphthalene. So looking at the stoichiometry of the reaction, 2-naphthol and 2-butoxynaphthalene are present in a 1-to-1 ratio. So from this you can calculate the theoretical yield, and the theoretical yield was calculated to be 0.75 grams. And the actual yield was 0.29 grams in this experiment. So from this you determine the percent yield to be 38.7%. So continuing the discussion from earlier on the reaction mechanism present in the synthesis of 2-butoxynaphthalene, we look at SN1 versus SN2 reaction mechanisms. So in SN1, the leaving group leaves first, which generates a carbocation, and then after the leaving group is left, the nucleophile attacks. Whereas in SN2, the leaving group leaves and the nucleophile attacks at the same time. It's also noted that in SN1, it's usually not a very strong nucleophile attacking the substrate, whereas in SN2, is usually a very strong nucleophile as well as a good leaving group that can stabilize the charge. So the presence of a strong nucleophile and a stable leaving group in SN2 reactions is what results in the nucleophile attack and the exit of the leaving group occurring simultaneously. So using this knowledge of the two different reaction mechanisms and applying it to the synthesis of 2-butoxynaphthalene, we can see it is a SN2 reaction. This is because in the first intermediate step, you see the generation of a 2-naphthoxide ion, and that is the nucleophile in this case. And the 2-naphthoxide ion is a very strong nucleophile. As well as you see the leaving group is the iodide ion from the 1-iodobutane. And the iodide ion can stabilize the charge very well. It's a stable ion. So both of these things, the combination of a strong nucleophile, the 2-naphthoxide ion, and a stable leaving group, the 1-iodobutane, point to the fact that this is an SN2 reaction. So finally, for question 4, we will be analyzing all methods of purification and characterization which were a focus in this course. We start by looking at methods of purification, beginning with recrystallization. So recrystallization is used to isolate and purify solids of interest. However, it cannot be used for liquids. There are 5 steps in the recrystallization process, starting with solvent selection, which is imperative for the recrystallization. To choose the ideal solvent, solvents are compared, and the appropriate solvent will have little to no solubility at room temperature and very high solubility when heated. Next, we dissolve the solid using the selected solvent. Then we perform a hot gravity filtration to remove insoluble impurities from the solution, leaving only the solid of interest. Then we crystallize the solid by cooling the solution slowly and then further with an ice bath to reduce the solubility and force the solid out of the solution. Finally, we isolate the crystals using a suction filtration. The flowchart on the right is displaying the recrystallization procedure for the online lab purification and characterization of solids. I'm not going to go into it because it contains too much detail, but it is there for you to see. The next method of purification is distillation, which is used to purify or isolate liquids. It also provides useful data on the boiling point of compounds, which can be used to identify compounds. The first method of distillation is a fractional distillation, in which a mixture of liquids can be boiled off and collected individually in the order of their boiling points. This is generally used for liquids with boiling points of a closer range. The second method of distillation, and the only one practiced throughout this course, was simple distillation, in which you separate 2 liquids into their components based on their boiling points. This is generally used for liquids with widely differing boiling points, such as around 50 degrees Celsius. This distillation can be used to remove a solvent from a solid or a liquid, or it could be used to purify a liquid by boiling it off and collecting it. The image on the right is showing the setup used in a simple distillation. Boiling the liquid in a distillation flask, which is attached to a condenser, which drips the condensed liquid into a collection flask. The boiling point can be obtained from the distillation, which can be used to help identify the compound. Another method of purification is the liquid-liquid separation, which is used to separate two immiscible liquids, each containing dissolved solutes. This can be used to isolate solids of interest or liquids as well. The first method of liquid-liquid separation is washing. As discussed in question 1, washing is using a washing solvent to remove any unwanted solutes and leave the desired solute in the separatory funnel. The second method of liquid-liquid separation is extracting. As discussed in question 1, extracting is using an extracting solvent to remove the desired solute and leave the unwanted solutes in the separatory funnel. The image on the right is depicting a liquid-liquid separation setup. The next method of purification is one of the most commonly used, filtration, which is used to isolate a solid or a liquid. The first method of filtration is a suction filtration, which uses a vacuum to pull liquid through a Buchner funnel. A suction filtration is used to isolate a solid from a liquid, as it leaves the solid dry. The filtrate is usually not of interest in a suction filtration. The second method of filtration is a gravity filtration, which uses gravity to pull liquid through a filter paper, leaving the solid behind. This is usually used to isolate a liquid from a solid, as it removes all the solid from a liquid but does not dry the solid in the filter. The filtrate is usually of interest in a gravity filtration. On the bottom, there's a drawing of a suction filtration apparatus and an image of a gravity filtration setup. The final method of purification of focus in this course is the rotary evaporator, otherwise known as the rotovap. This is used to isolate a solid or a high boiling point liquid from a solvent. It is an advanced form of distillation. It uses pressure in a heated water bath to boil compounds at lower temperatures than they normally would boil at. It can be used to evaporate water and low boiling temperature solvents, leaving behind either dry solids or pure high boiling liquids. The main use for this is purification or isolation of solids or liquids. That concludes the discussion on methods of purification focused on throughout this course. So next we move on to methods of characterization discussed throughout this course, beginning with chromatography, which can be used to assess purity and identify solids and liquids based on comparison to another solid or liquid. There are many forms of chromatography, but this course focused on two in particular, starting with thin layer chromatography, or TLC, which has three main uses: to determine the purity of a compound of interest, to identify an unknown compound, and to monitor the progress of a reaction. Chromatography consists of a mobile phase, or a solvent with the sample, and a stationary phase, or the absorbent through which the mobile phase moves. In the case of TLC, the stationary phase is the silica gel on the alumina plate, and the mobile phase is an eluent or solvent containing the sample, which will climb up the plate through capillary action, carrying the sample with it. The sample separates into its components while it moves. The distance traveled by each component depends on the polarity of the component. The more polar, the shorter the distance traveled. When a compound is separated, it will appear as a column of spots. These spots can be compared to other samples spotted on the plate. This can be used to determine the purity of a compound based on how many spots there are in a column, or the identity of a compound based on the location of the spot of an unknown compared to the location of a spot of a suspected identity, or to determine the progress of a reaction by comparing a product spot with a reactant spot. The other form of chromatography of focus is gas chromatography, or GC, which is used to determine the identity of liquids only, not solids. It can also be used to determine concentrations of unknowns using standard curves. In the case of GC, the stationary phase is coated on the inside of a metal column, while the sample is pushed through by air, which is the mobile phase. Compounds will flow out of the column in different amounts of time due to several different factors, including boiling point, functional groups, and many other factors. The compounds will show up as peaks on a chromatogram, separated by their retention times. Chromatograms will provide retention times which can be used to determine an unknown identity by comparing retention times to a standard. They will also provide the integration area of the peaks, which can be used to determine concentrations of unknowns. The next method of characterization is spectroscopy, which can be used to determine the purity and the identity of solids and liquids based on literature data. Spectroscopy provides data about functional groups present in the sample. There's two forms of spectroscopy analyzed in this course: IR spectroscopy and NMR. IR was used in this course while NMR was not. IR, or infrared spectroscopy, uses infrared light to measure the energy required to vibrate molecular bonds in the sample, and plots the man's percent transmittance against wave number in an IR spectrum. This can be compared to literature data to identify functional groups present in the compound. NMR, or nuclear magnetic resonance, measures how shielded atoms in a compound are from an external magnetic field, and plots the data on an NMR spectrum. The chemical shifts displayed on an NMR spectrum can be compared to literature values to determine functional groups. The final method of characterization is using experimentally measurable physical properties of compounds. These can be used to determine the purity of a compound and its identity based on comparison with literature data. The first relevant physical property used is the boiling point of liquids, which can be compared to literature values of boiling points to help determine the identity of a compound, or its purity. As a pure liquid will usually have a boiling point range of around 2 degrees Celsius. The second relevant physical property used is the melting point of solids, which can also be compared to literature values of melting points to determine identity or purity of a compound. In using melting point to determine purity, a pure compound usually has a sharp melting point varying only by 1 to 2 degrees Celsius, while a compound containing impurities can have a vastly broadened melting point. These are the references that I used for my report, and this concludes my report. Thank you for your time, and I apologize for going over the limit, and I ask you to be lenient with me as it was a lot of information to include in a small amount of time. Thank you in advance, and goodbye.